If you've been tracking the latest AI research, you've probably noticed a quiet but massive shift happening under the hood. The transformer architecture, which has powered nearly every major language model breakthrough since 2017, is finally hitting its theoretical and practical limits. And that's why researchers are rapidly pivoting toward a completely different mathematical framework, state-space models, with Mamba leading the charge. To understand why this matters, we need to step back and look at what's actually happening inside a transformer. At its core, the transformer relies on self-attention. Every token in your input sequence computes a relationship with every other token. That's beautiful for capturing long-range dependencies, but it comes with a quadratic computational cost. Double the sequence length, and you're dealing with 4 times the work. That's why we need massive GPU clusters, why context windows are expensive to extend, and why inference latency becomes a real bottleneck as models scale. State-space models take a fundamentally different approach. Instead of computing pairwise relationships across the entire sequence, they treat the input as a continuous signal and pass it through a linear time-invariant system. In plain terms, the model maintains a hidden state that summarizes everything it has seen so far and updates that state sequentially as new tokens arrive. The math here is elegant. You're essentially solving a differential equation over discrete steps. The computational cost scales linearly with sequence length, not quadratically. That means you can process millions of tokens without the memory explosion that plagues attention-based architectures. But early-state space models had a critical flaw. They were too rigid. The hidden state would compress information uniformly, which meant important details could get washed out over long sequences. Mamba solved this with a mechanism called selective scanning. Instead of applying a fixed transformation, the model dynamically adjusts its own parameters based on the input token. Think of it like an adaptive filter that decides what to remember, what to forget, and what to pass through in real time. This selective behavior lets the model preserve critical context while still maintaining that linear scaling advantage. Now you might be wondering, if linear scaling is so much faster, why didn't we use this architecture earlier? The answer lies in training efficiency. Sequential computation is great for inference, but terrible for parallelizing across thousands of GPUs. Transformers win on training speed because attention can be computed in parallel across all token pairs. Mamba originally struggled here, but recent breakthroughs in parallel scan algorithms have closed that gap. By reformulating the recurrence relation into a divide-and-conquer structure, researchers can now compute the entire hidden state trajectory simultaneously during training, while still falling back to fast sequential decoding at inference time. It's a hybrid approach that gives you the best of both worlds. The research community is already putting this to work. We're seeing hybrid architectures that use attention for short-range reasoning and state-space layers for long-range context. We're seeing models that dynamically switch between mechanisms depending on the task. And we're seeing massive improvements in throughput and memory efficiency without sacrificing accuracy. The implications for AI scaling are profound. If we can decouple performance from quadratic context scaling, we finally have a path toward models that can process entire books, code bases, or video transcripts in a single pass without breaking the bank. This isn't just an incremental improvement. It's an architectural paradigm shift that's already reshaping how we think about sequence modeling, memory efficiency, and the future of large-scale AI. If you want to dive deeper into the math behind selective scanning, the parallel scan implementations, or the latest benchmark comparisons, I've linked the key papers and technical breakdowns in the description. The next generation of AI isn't just about bigger datasets or more parameters. It's about smarter architectures. And if you're serious about staying ahead of the curve, you need to understand what's coming next.